Welcome to Yatim Khana and Madrasa Anjuman Khairul Islam's Pune College of Art, Science and Commerce Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Students, today we are going to study the topic which is called as why PN Junction Diode does not obey Ohm's law and why fixed value resistor, which is a two-terminal resistor, obeys Ohm's law. So it is a very simple topic, but it required to be understood because the behavior of the PN junction diode is non-linear, and that is the reason why the PN junction diode does not obey Ohm's law. But we'll study that by applying certain voltages and with the help of some logic. So first of all, what we'll do, we'll study why fixed value resistor. So all of you know that fixed value resistor is also called as two terminal resistor. Why fixed value resistor into bracket two terminal resistor obey Ohm's law? So this is our today first target, and then secondly we'll come down to the PN junction diode. So first of all, let us try to understand what is Ohm's law. This Ohm's law you are studied in 10th standard, in 12th standard, and again we are repeating in FY BSc also. So Ohm's law is what? The statement of the Ohm's law starts from as long as physical state of conductor remains same. So this is very important. As long as physical state of the conductor remains same, the current flowing through the conductor is directly proportional to applied voltage to conductor. The current flowing through the conductor is directly proportional to the applied voltage to conductor. But condition is what? As long as physical state of conductor remains same. Therefore, here we write normally current is directly proportional to applied voltage V. So here current is directly proportional to applied voltage V. If R is the proportionality constant, let us consider R means resistance is the proportionality constant, then V is equal to I into R, and this is Ohm's law. This is Ohm's law. So normally what we do, write a statement of Ohm's law which is wrong. So I have written here and have put a cross mark with the red color. Normally we simply say current flowing through the conductor is directly proportional to the applied voltage to the conductor, that we say. But it is not correct statement. Why? Because first of all, we have to consider whether the physical state of conductor means as long as physical state of conductor remains same, that law is applicable. So here simply if you write the current flowing through the conductor is directly proportional to the applied voltage to the conductor, then it is wrong because you have not mentioned here whether the physical state of the conductor is remaining same or not remaining same. Therefore, the correct statement of Ohm's law is here: as long as physical state of conductor remains same, the current flowing through the conductor is directly proportional to the applied voltage to conductor. And this is the right statement. So we have to start from what? About the physical state of the conductor, it should remain same. So now let us consider what we know that the symbol of fixed value resistor is a two terminal resistor. All of you know terminal A and terminal B, and this is the symbol of fixed value resistor. And its electrical value, what is the fixed value resistor? It is a resistor which is having electrical value fixed, and its electrical value between its two terminal A and B is fixed, means constant. Actual resistor looks like this. So in laboratory, if you handle the resistor, then you will come to know that actual resistor would look like this. There will be different color bands. So here there is a last color having a long gap between this. This is the tolerance color, and these are the colors for the calculating the value of resistor. So in this way here, two terminal resistor is having electrical value fixed between its two terminal, namely A and B. Now what we'll do it here, our target is what we want to study, that why fixed value resistor obeys Ohm's law. Why fixed value resistor obeys Ohm's law. So now what we do it here, let us consider the resistor of 1 kilo ohm. Let us consider the resistor of 1 kilo ohm. Of course, we are talking about a fixed value resistor between terminal A and terminal B. The value of this resistor R is fixed, that is 1 kilo ohm. So let us consider the resistor of 1 kilo ohm connected to variable voltage source of 1 volt to 10 volt. So as shown in this diagram, now here see, we have taken a fixed value resistor, and this fixed value resistor is having its value between terminal A and B as a 1 kilo ohm. And we have connected the variable voltage source to this resistor, which is varying from 1 volt to 10 volt. And we connected the current meter, that is ampere meter, to measure the current flowing through this circuit. Now all of you know that when you connect the voltage source 1 volt to 10 volt to the resistor, the current will flow from positive of the battery to the negative of battery through the resistor, because here circuit is completed. And in this way here, current will start flowing through this circuit for all applied voltages from 1 volt to 10 volt. But remember, when applied voltage increases, no doubt that the current flowing through the circuit will also increase, because we have kept the resistor value constant, that is 1 kilo ohm. So this is very simple circuit of the 10 standard. So now let us see here. In above diagram, the circuit will, in above diagram, the current will flow through the resistor from terminal A to terminal B for all applied voltages from 1 volt to 10 volt, because the resistor is what, a passive component, and it passes current in both direction. Now we have connected it in this direction, positive to the upper terminal A of the resistor and negative to the lower terminal B of the resistor. So current will flow for all applied voltages from 1 volt to 10 volt. So the current flowing through the resistor, now here in this diagram our resistor is a conductor. The current flowing through the resistor, into bracket we have written conductor because it passes the current. The current flowing through the resistor is directly proportional to the applied voltage, because physical state of resistor, that is conductor, state of the conductor, that is a resistor, remains same. It is the same, means the value of resistor is fixed or constant. So physical state of conductor means value of resistor, is fixed or constant. So we are not changing the value of resistor. Therefore, that is what in this diagram, in this paragraph it is mentioned, the current flowing through the resistor, where the resistor is our conductor, is directly proportional to the applied voltage, because physical state of resistor, which is our conductor, means the value of resistor is fixed, that is constant, that is a constant. The value of resistor does not changes when applied voltages to the resistor is changed from 1 volt to 10 volt or any other volt. Here in our example case, we have taken the example of what? 1 volt to 10 volt. So you apply 1 volt to 2 volt, 5 volt, 8 volt, 9 volt, 10 volt. The value of resistor which we selected is 1 kilo ohm, means it will remain 1 kilo ohm only. It will not change for all applied voltages from 1 volt to 10 volt, or if you take 1 volt to 20 volt, any other example accordingly. By using Ohm's law, what we can do it now? We will use the Ohm's law, V is equal to I into R. Let us calculate the current flowing through the resistor of 1 kilo ohm, for all applied voltages from 1 volt to 10 volt. And it's very simple. By using Ohm's law, we have to calculate the current flowing through this resistor. For 1 volt, for 2 volt, for 10 volt, and for all these in between voltages, we will calculate the current. So the logic is very simple. So first of all, let us see here, V is equal to I into R. First of all, we will calculate current for 1 volt. So 1 volt is the voltage. We want to calculate the current I. Value of resistor is 1 kilo ohm. Therefore, in the next step, it will be I is equal to 1 volt divided by 1 kilo ohm, and it will result into 1 milliampere. So for 1 volt applied voltage to the resistor of 1 kilo ohm, the current flowing through the resistor will be 1 milliampere. And this is a very simple mathematics of the 10th standard. Similarly, we can calculate for all other value of voltages the current flowing through the resistor. And here you will get a graph. Here you will get a table, voltage in volt applied to the resistor 1 volt to 10 volt, and current flowing through the resistor for respective applied voltage is 1 milliampere, 2 milliampere, and accordingly last for 10 volt the current will be 10 milliampere. And now after completing this small experiment, what we will do it, we'll plot the graph. So now let us see here, let us plot the graph of current versus voltage. So on y-axis we have taken the current, on x-axis we have taken the voltage. 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, and like that up to 10 volt. And on y-axis, for 1 volt we got current 1 milliampere, for 2 volt we got the current 2 milliampere, for 3 volt we got the current 3 milliampere, and like that if you plot the graph, you will get the graph which is a straight line number 1. Number 2, it is passing through origin. Number 2, it is passing through origin. And in this way, this graph will be there as long as R is equal to 1 kilo ohm and we have applied the voltages from 1 volt to 10 volt. So as shown in above graph, as shown above, the graph is a straight line passing through the origin. Graph is a straight line passing through the origin, and therefore the resistor obeys Ohm's law. And therefore the resistor obeys Ohm's law, because what? As long as physical state of conductor remains same, the current flowing through the conductor is directly proportional to applied voltage. And here the straight line indicates that the current is proportional to the applied voltage. Straight line indicates that the current is flowing to the applied voltage. Why it is straight line? Because physical state of conductor is same, means value of resistor is not changing for all applied voltages from 1 volt to 10 volt. And that is what simple. Therefore the resistor, of course fixed value resistor, obeys Ohm's law. Now let us proceed here. Why PN junction diode does not obey Ohm law? Why PN junction diode does not obey Ohm's law? So here let us consider now, as shown below, let us connect the diode D to the variable voltage source of 1 volt to 10 volt. So same experiment we will do with the diode, whatever we have done with the resistor. We have taken a fixed value resistor of 1 kilo ohm, we applied 1 volt to 10 volt and we measure the current and we plotted the graph. Now same thing we'll do with the diode. We'll take a diode, PN junction diode, and we'll apply the variable voltage 1 volt to 10 volt to that PN junction diode as shown here. So it is very simple. So diode is there, anode of the diode, cathode of the diode, this horizontal line, terminal A and terminal B we have shown here. So this is terminal A and terminal B, not A means not for anode. So here this diode is connected to the 1 volt to 10 volt battery. Battery is connected such that positive of battery is going to the anode of the diode and negative of battery is going to the cathode of diode, and voltage we are applying from 1 volt onwards, means which 1 volt is greater than 0.7 volt. So for all these voltages 1 volt to 10 volt, no doubt the diode will conduct and current will start flowing through the diode. For all these voltages from 1 volt to 10 volt, no doubt that the diode will conduct and current will start flowing through the diode. So this is A means ampere meter, that is current meter we have taken here. Now let us see here. We know that the resistance of diode goes on decreasing when applied voltage increases, because this already we have studied. PN junction diode is a what component? Semiconductor component. And when we apply the voltages to the PN junction diode, which is 1 volt, 2 volt, 5 volt, 7 volt, 9 volt, 10 volt, as applied voltage increases, current flowing through this circuit no doubt increases. But here diode is a semiconductor component. Diode is a semiconductor component and its resistance decreases, where in this case also the current flowing through the circuit for 1 volt to 10 volt increases, but the value of resistor are 1 kilo ohm, means 1 kilo ohm only for all applied voltages, because it is a fixed value resistor which is a two terminal resistor. Whereas here now our diode is a semiconductor component. Diode is a semiconductor component, and that is what here written. We know that the resistance of the diode goes on decreasing when applied voltage increases. Therefore, the current flowing through the diode D is not linear, is not linear for all applied voltages from 0 volt to 10 volt, and the graph is not straight line passing through origin, and graph is not a straight line passing through origin. And that graph, you know, that graph is nothing but IV characteristics of PN junction diode in forward bias condition, because here the diode is forward biased. Anode is connected to positive of battery, cathode is connected to negative of battery, and voltage applied to diode is starting from 1 volt to 10 volt, means much more greater than 0.7 volt onwards. So in this way here the graph will be like this. So current flowing through the diode and voltage across applied to the diode, or across the diode if you plot the graph. So this graph is, you know, forward bias characteristics of PN junction diode, and this curve you see here, This curve is an exponential curve. Now, why this curve is exponential? Because this curve is exponential because inside PN junction diode there is a junction capacitor. Inside there is PN junction diode, there is a junction capacitor, and when you apply the DC voltage to the diode, means to the junction capacitor, that capacitor exponentially charges. So it is a very simple logic. So, or otherwise you remember that the diode IV characteristics of the diode are what? Till zero point 0.6 volt the current is 0, and after zero point 0.6 volt the current starts increasing in this direction like this, and this is the graph. Now this graph is a highly non-linear. This graph is highly non-linear because till zero point 0.6 volt the diode is not conducting only, and then after zero point 0.6 volt, even though it is conducting, the graph is not a straight line. Or there is one more way to plot the graph. So like this also, zero point 0.6 volt up to there is a 0, and if you say that it is applied 1 volt onwards, then for 1 volt the current is different, for 2 volt the current is different, for 3 volt the current is different, and in this way here the current is not proportional to the applied voltage. Current is not proportional to the applied voltage. One more graph we'll see here, which you have studied in forward bias characteristics. Till zero point 0.6 volt it is 0. From 0.7, zero point 0.6 volt it goes on increasing, and it is like this. So this is the, you see in every forward bias characteristics, this curve you remember, this curve is exponential. This curve is exponential. So whenever you draw the forward bias characteristics of the PN junction diode, you'll observe the exponential curve, and that is what junction capacitors behavior. Now, this paragraph will tell you everything. The current flowing through the diode is not linear because the value of forward resistance, of PN junction diode changes when applied input voltage to the PN junction diode is changed. The resistance of PN junction diode decreases. The resistance of PN junction diode decreases when applied input voltage. When input voltage applied to PN junction diode is increased because diode is a semiconductor component. Because diode is a semiconductor component. As explained above, the physical state of conductor. Physical state of conductor means what? Resistance of PN junction diode. So as explained above, the physical state of conductor means resistance of PN junction diode is not constant, because as applied voltage goes on increasing, the resistance of PN junction diode goes on decreasing, is not constant, and graph is non-linear. Graph is highly non-linear. Therefore, PN junction diode does not obey Ohm's law. PN junction diode does not obey Ohm's law, and in this way, this is a very simple phenomena why PN junction diode does not obey Ohm's law. Now, today one more thing I am going to explain you, which is very funny, but it is very, you can say that, interesting. So all of you know now that a PN junction diode having anode terminal, having cathode terminal, and inside PN junction diode there is a barrier potential. There is a barrier potential. Barrier potential is having what? Negative barrier potential is to the anode and positive barrier potential is towards the cathode. And because of this barrier potential, all of you know its magnitude for silicon is 0.7 volt. Because of this barrier potential only, the PN junction diode starts conducting above after 0.7 volt. After 0.7 volt ideally, and at room temperature it starts conducting at 0.6 volt. But now let us see here, look at on the right hand side only, this portion. A 10 volt battery is taken and positive of the battery is connected to the anode, negative of battery is connected to the cathode. And now 10 volt battery is much more greater than the minimum voltage required to forward bias the PN junction diode. The minimum voltage required to forward bias the PN junction diode, means to force the diode into conduction, is 0.7 volt. Therefore, this voltage is much more greater than this, and therefore as soon as you connect 10 volt battery to the PN junction diode such that anode to the positive and cathode to the negative, the diode is conducting. Diode is conducting, and then if you connect the voltmeter across the PN junction diode such that positive of voltmeter to the anode and negative to the cathode, the voltage measured across PN junction diode, is zero point 0.7 volt only, is zero point 0.7 volt only, and voltage above the 0.7 volt, voltage above 0.7 volt, that is 9.3 volt, that is 9.3 volt, is short circuited by the diode, and that is the drop across the diode, because diode is heavily conducting. And when you say the diode is heavily conducting, diode is a semiconductor component, it short circuits the voltage above the zero point 0.7 volt. Now look at the left hand side. Now this is very funny or magic. You'll say the battery is of 10 volt, and positive of battery is connected to the voltmeter on the left hand side, negative of battery is connected to the negative of voltmeter. So here positive of battery is connected to positive of this voltmeter, negative of battery is connected to negative of voltmeter. And if you look at only on the left hand side this much, then you will say this voltmeter should measure 10 volt, but it is not measuring 10 volt. This is also measuring zero point 0.7, and this is also measuring zero point 0.7. The voltmeter connected across diode is also measuring zero point 0.7, and voltmeter connected across battery is also measuring zero point 0.7 volt. Why? What is the reason? So here is the understanding of electronics. Positive of this voltmeter and positive of that voltmeter both are connected to the anode of the diode as well as positive of battery. Positive of left hand side voltmeter and positive of right hand side voltmeter both are connected to the anode of the diode as well as positive of battery. See, positive of battery as well as anode of diode, and therefore this terminal is short circuited terminal, means they are connected to each other, and therefore whatever major voltage measured by this voltmeter, same voltage will be measured by this voltmeter. So this diagram is very simple but very interesting. Negative is connected to the negative of battery, negative is connected to the cathode of battery. This voltmeter also negative is connected to negative of battery, negative is connected to cathode of battery. Means this negative terminal is also common terminal between both voltmeters. Positive terminal is also a common terminal between both voltmeters, and which is connected to the batteries plus as well as this. Now the question comes here, if this voltmeter, if we feel that this voltmeter should measure this as a 10 volt, should measure this as a 10 volt, then what can be done? Because you will say, no, we want this voltmeter to be measured as a 10 volt, not as a 0.7. Okay, this is all right. We are measuring across diode. So let this voltmeter measure the voltage across diode, that will be 0.7 volt. Whenever diode conducts after 0.7 volt, the voltage across diode is 0.7 volt. Now, to have this voltage measurement as a 10 volt, what should be done? So logic is very simple here. Why this is also measuring the same voltage this? Because positive of this and positive of this are common. Positive of this and positive of this are common. So if you separate them from each other, if you separate them from each other by connecting a resistor in between these two terminal, in between these two terminal means positive of battery and anode of the diode, then your job will be done. And that is what here, see diagram. We'll connect the resistor R. We'll connect the resistor R between anode of the diode and positive of battery. Between anode of the diode and positive of battery. And now you see here, positive of this voltmeter and positive of this voltmeter are not now common, are not now connected to each other. They are connected to each other through the resistor, and therefore now your problem is solved. This voltmeter now is directly connected across the diode, and it will measure 0.7 volt. This voltmeter is now directly connected to the battery, and this will measure 10 volt. Now what is the problem? What was the problem? Earlier when this resistor was not there, both of them were having positive terminal as a common, and we have separated now that by connecting resistor over here in this case. And this is a very simple solution. The resistor isolates this point and this point, isolates this point and this point. So in this way here it is very simple. Similar way here one more diagram is there. So in this diagram the barrier potential is shown for the explanation why there is a 0.7 volt. Now it is not necessary, all of you know, whenever anode of the diode is connected to positive battery and cathode of the diode is connected to negative battery, and battery voltage is greater than 0.7 volt, here 1 volt to 10 volt, then diode gets forward bias and voltage across diode VD, positive to the anode, negative to the cathode, will be 0.7 volt. Look at the left hand side. Again, what is here? Same thing. This left hand side voltmeter is connected to the battery. positive of voltmeter to the positive of battery, negative of voltmeter to the negative of battery, voltmeters negative to the negative of battery. But this voltmeter is not measuring 10 volt, 1 volt to 10 volt. This voltmeter is not measuring 1 volt to 10 volt. It is also it is measuring zero point 0.7 volt only. So, and what is the problem? Problem is here only. See here. Positive of this voltmeter goes to positive of this voltmeter, means both terminals are now common. Therefore, this voltmeter is also measuring the voltage across diode. This voltmeter is also measuring the voltage across diode. This voltmeter is also measuring the voltage across diode. And in this here, the diode is forward biased by the voltage 1 volt to 10 volt, and diode is conducting. Therefore, here this voltage is zero point 0.7 and this also zero point 0.7. Now, if you feel that again same thing, this voltmeter should measure this as a variable 1 to 10 volt. Then here there should be separator, means this terminal positive and this terminal positive should not be common, should not be common. So here they are common to each other now. So here this is now resistor R in between, that between anode of the diode and positive of battery. Now when you vary this from 1 volt to 10 volt, suppose it is 1 volt, applied voltage to diode 1 volt means greater than zero point 0.7 volt. So diode is conducting, and therefore voltage across diode is always zero point 0.7 volt, because minimum voltage is here 1 volt. Minimum voltage is 1 volt, not from 0 to 0.7, 0 to 10. So minimum is 1 volt. So 1 volt is much more greater than zero point 0.7 volt. So like that. So here positive of voltmeter now, sorry, positive of the battery is connected to the positive of voltmeter on left hand side, and negative of voltmeter is to negative of battery. And here this voltmeters positive and this voltmeters positive now are not common, are not common. They are separated by the resistor R, and therefore this voltmeter now you see here, if you vary the voltage of this battery from 1 volt to 10 volt, then this will also measure whatever voltage of the battery, 1 volt 1 volt, 5 volt 5 volt, 8 volt 8 volt accordingly. But here this voltmeter is directly connected between anode and cathode of the diode. Therefore, here whatever voltage 1 volt to 10 volt, the voltage across PN junction diode, which is forward biased, is always zero point 0.7 volt. And our problem is solved. We have used the resistor R to separate the positive of this voltmeter and positive of this voltmeter. Now they are not common. Therefore, this voltmeter will now measure the voltage of battery, and this voltmeter will measure the voltage across diode, that is VD. So it's a very simple concept. So thank you very much for watching this small video. With the help of this, you will get a lot of understanding about the PN junction diode's behavior, and voltage measurement across the PN junction diode, and separation of what two voltages with the help of a resistor R. Thank you.